10, 9, ignition sequence starts. 6, 5, 4, 3, 2. Liftoff. We have a liftoff. Liftoff on Apollo 11.
When the moon launch happened, I was very young, but I remember the excitement.
There was something fundamentally new in our own understanding of ourselves as species on this planet, represented by looking at Earth from outside.
When you could see the Earth as a whole, you recognize that everything on the Earth is connected to everything else.
It was a critical piece of the story of why the environmental movement emerges in 1970.
Earth Day, a day dedicated to enlisting all the citizens of a bountiful country in the common cause of saving life from the deadly byproducts of that bounty.
We had rivers that would catch on fire
because of the garbage and pollution in it, DDT and the harmful impacts it was having on lots of birds and fish.
The bald eagle, our national symbol, was nearly extinct.
America must undertake a revolution in its way of life to clean up the mess each of us has made.
The challenge was profound. Princeton had one of the most ambitious responses. In fact, the last half-century of research at Princeton in environment can be thought of as one big gulp of excitement, leadership, innovation.
Environmental research on Princeton, at Princeton really started with Rob Sokol in the 70s.
Rob was one of a couple of academics who I think of as environmental prophets. They understood, before others, just how serious these problems were and that they weren't going away.
And I came to Princeton in '71 with a mandate to invent interdisciplinary environmental research, find problems that would require collective responses from several parts of the campus. One of them was about energy efficiency in buildings. In the 1950s and 60s, energy use was equated with prosperity. And so the question was, this prosperity doesn't come free. And one can ask whether the same levels of services could be accomplished with less energy. It seems an obvious question now, but it was a kind of subversive question in 1971.
And so Rob started a center here focused on a wide variety of energy and environmental problems. And that effort allowed Princeton to seamlessly jump into the middle of the applied aspects of the climate problem.
Princeton has a secret weapon in another institution just a few miles away called the Geophysical Fluid Dynamics Lab. I think that's the worst name I know for any institution.
A mouthful. We'll call it GFDL. Inside the GFDL, two luminary scientists, Suki Manabe and Dick Weatherall, made the world's first climate model. A model of 3 different components on Earth that collectively determine our climate: the atmosphere, the oceans, and the land surface.
The importance of climate modeling is to figure out what factors, what equations can explain what we know happened in the past, and then sort of turn the crank forward and see where does that take us in the future.
It's the best tool. In some sense, it's the only tool we have for doing reliable projection of what the future looks like. How sea level, how flooding, how extreme heat will interact with human beings and society, which can be used for society to defend themselves. And that's the kind of influence that makes a difference.
Because of the center of activity on climate in Princeton and the partnership between GFDL and the university, many others were attracted here across the whole sweep of what is now called climate science. There's George Philander, who studied El Nino and La Nina, and became one of the most prominent climate scientists in the world.
Princeton has put a lot of effort into studying CO2 in the ocean, the atmosphere, and the terrestrial system as well. What Michael Bender and John Higgins wanted to do was find the oldest ice, because ice preserves the composition of the atmosphere at the time that it was formed. What Bender did was develop a way to actually date the ice using argon isotopes. We don't know what the oldest ice is, but so far they've got 2 million years, which is pretty old for an actual physical record.
So we have an incredibly diverse and interdisciplinary approach to the problem, which really is fairly unique to Princeton.
It started full force with the Princeton Environmental Institute that really facilitated that communication between engineers and scientists and the larger community.
I've been here about 9.5 months, and I've found that the barriers are almost non-existent to collaborating.
Humanities, economics,
social scientists, political scientists,
Biology and ecology.
Environmental policy.
It was always important, but it's critically important now to bring the pieces together. In my own field of urban systems, we look at not only individual cities, but how cities affect the entire planet.
The university has a field station called Impala, which is located in central Kenya, and has been a hub of both research and undergraduate education for several decades now. With respect to biodiversity, the planet is not doing so well. How do we protect wildlife and wildlands in an increasingly hot, crowded, and hungry world? That collaboration across multiple disciplines, that's the only way we're going to really address these concerns.
And Princeton continues to build. Recently, it established the Endlinger Center that is dedicated to producing alternative energy to solve the carbon and climate problem.
a lot of what we do today is built on all this legacy that had happened in the 70s and 80s. Innovating and developing new measures to improve energy efficiency in buildings, to emerging solar cell technologies, to new battery chemistries. One way to view the climate challenge is really looking at it as an energy challenge that's wrapped up in the carbon challenge. The energy sources that we use today, more than 80% is fossil fuels.
And one of the key questions becomes, how quickly can we transform to be less dependent on the fossil fuels and more dependent on carbon-free fuels? And Princeton, from the very early days, has been a leader in trying to figure out the answer to that puzzle.
Princeton researchers have achieved a major milestone. Their test reactor produced 3 million watts of fusion power, a new world record.
Fusion is technically a nuclear reaction that happens when two atoms are crushed together and form a helium nucleus. And when that happens, a little bit of the mass is lost and converted to pure energy. And so at the Princeton Plasma Physics Lab, for the first time, they were able to, what amounts to lighting up a star in Princeton, New Jersey.
It's one of the few zero carbon energy source. And so if we can figure out a way to do this sustainably, economically, it lays the pathway for us to get to a zero carbon economy.
Yeah, there'll be no pollution in that land. Be no pollution in that land.
If there hadn't been that activity over the last 50 years, we wouldn't be in the position we are now to solve the climate problem. The long-standing tradition here with luminaries that attracted other luminaries means capability in the present day.
It's a huge opportunity where Princeton is really set up wonderfully to lead for the next 50 years.
Especially making me hopeful is the urgency and the passion that the younger generation is feeling.
This is the NSTX test cell. This is where all the magic happens.
The younger people have this fire in the belly. They see themselves as being impacted by climate change. And they see it much more as how can we collaborate to solve some of these grand challenges.
Environmental challenge facing humanity right now is survival of the species. In order for the species of humans to survive, the rest of the planet has to survive.
A new problem, not present at the beginning, called polarization, which is making every dialogue more complicated. There's nothing Republican about a cloud or Democratic about sea level rise. What I wish is that universities can distinguish themselves in depolarizing the conversation.
We've got the stuff we need right now. Let's just do it. Let's just do it.